let's just start. Yeah, welcome everybody to this talk about effective debugging and profiling of Qt applications. My name is Volker Krause. I work for a company called KDAB. We do all kinds of Qt services, training, consulting, development, mentoring, whatever you need as long as it's related to Qt. I don't want to bore you anymore with marketing details about our company. We have a booth over there, so if you're interested, come visiting us. So let's just get started with the, it's not updating on my screen, the stuff we will be seeing in the next hour. We will be looking at debugging and profiling tricks, tools, and techniques specifically for dealing with Qt applications. So how can you use common debugging and profiling tools out there together with Qt in a more productive way? Or what tools are built into Qt that you can use to improve debugging and profiling? And we will see some domain-specific tools for some of the higher-level frameworks in Qt to help you debug those. We will not look so much into details regarding profiling of Qt quick applications. I have another talk right after this, which exclusively focuses on profiling Qt quick. We'll look into this there in more detail. The most easy way, classic way to do debugging is, of course, printf debugging. You just write some debug output. Very easy, but what does Qt give us there to support us? You probably know QDebug, QWarning, QFatal, the debug output mechanisms in Qt. In Qt, in a Qt application, they are usually nicer to use than printf or STL.io because they support the Qt types. So you can stream in most of the built-in Qt types, and they will be printed out in a meaningful way, which will not work out of the box with printf or STL. It will also, if you use the object pointers, will show you the type name and the object name if you have that set. So it's useful to include the QObject macro in your own classes, also to have a nicer debug output for pointers of this type. And of course, if you set the object name, which is only really relevant for testing or for debugging anyway, that will also be used by QDebug to give you more meaningful output. There's a few more interesting methods for printing out information about a Qt object built into QObject itself. And that is dump object info. That's the output we are seeing here. The interesting bit that contains is all inbound and outbound signal connections of that object. So you can check which of your signals are connected to where and which inbound signals are connected to your slots. So if you just want to verify, or if you're debugging a slot that's not called, you can verify that it's actually connected in this instance. Especially useful when you actually combine that with a debugger and call it at runtime. We'll see that in a bit. The second one is dump object tree. That gives you the entire object hierarchy, also on the debug output of the given QObject. That's useful for looking at widget hierarchies and dealing with layouting problems and something like that. But with all the debug output we add to our code, and the one that's already existing in Qt, you might run into debug output where you have no clue where it's coming from. It's informing you about some important error, but you don't actually know who added that or what's it for. So there's a number of tricks to find out where the debug output actually comes from. There's a macro defined in Qt, qfunc_info. If you just add that to the QDebug output, it will show the class name, the method name, and the line number of where that debug output was generated. So you at least find the place in the code correctly where this output is coming from. Sometimes just knowing where the output was triggered is not enough, but you actually want to capture the state of the entire application the moment this output was triggered. And there's an environment variable that you can enable, Qt fatal warnings, that will cause your application to assert whenever it hits the Q warning. So you can attach the debugger to that, and you get a break trace in the moment you hit a Q warning. Error condition somewhere in Qt, for example, and then you can analyze the state of your application and figure out why it's running into this scenario. And of course, you can also set a breakpoint on the actual output. And to capture that, there's an internal method in Qt, Qt message output. That's the one that actually writes to the screen. So that's the one you want to set the breakpoint on to get a meaningful backtrace. If you try that on QDebug, you might miss Q warning and Q fatal. And you capture it when creating the output stream, not when it's actually done with it. Yeah, I think that's all about the printf style debugging for now. So let's look at some more advanced debugging tools. The obvious choice, of course, is the classical instruction level debugger. Yeah, the easy way out is to use QtCreator. That has a nicely integrated debugger already that understands the Qt types. If you use any other instruction level debugger, you might run into the problem that your debugger is not understanding the internal data structures of your Qt types. So figuring out what's in a QString instance might actually be quite tricky because you have to look into the D pointer and then somehow understand the internal UTF-16 encoded data structures and somehow convert them into something that you can actually read, which is, yeah, not very effective. So luckily there are some extensions out there that enable you to, well, extend your compiler to your debugger to actually understand those types. For Visual Studio, there is a plugin provided by Nokia that adds support for Qt types to the Visual Studio debugger. You can find that at this address. It only works with the professional version, I think the one that actually supports plugins, so you can't use that with the free Express version of Visual Studio, unfortunately. For GDB, there's also a bunch of extensions available at the other URL. You can put that into your GDB init, and then it will automatically load it whenever you start GDB. And then you can use the various macros defined in there, like print Qt4 string to output the content of Qt types written by the guy over there. So yeah, in Creator you don't have the problem because Creator has all of that built in already. What else do we have? Yeah, remember the dump object info method we saw earlier to find out if a specific Q object is connected to a slot or to which slots and specifically a signal is connected, or the other way around, which signal is connected on your current slot. And you can call these methods at runtime while you are in the debugger. For this to work, you need access to the debugger command line, which you can get in Creator if you enable the view debug log which is kind of misleading because it's not actually a log, but it's an interactive command line where you can actually type in raw GDB commands. And in there, you can just, well, call dump object info on any QObject pointer you have, and you get in the second window, you get the output we saw earlier. For example, useful to find out if you had an emit statement, where is this actually going? In which order are the slots called, and is it actually connected? And yeah, having access to the raw debug console, of course, is useful for any other extension you have in your debugger that's not supported by Creator. Like looking into Objective-C types on macOS, for example, you might get your hands on Mac. Creator can't handle those, but you can use the Mac-specific extensions in Creator just by using the commands manually. Right, so that's pretty much the only Qt-specific thing regarding normal debuggers. Everything else is just the same. So what else do we have? Yeah, also slightly related to debugging. Often the problem you're debugging is actually caused by violating some assumption that the original author of the code made. So it's quite important that you actually document all these assumptions. And the best way to do that is using asserts. And Qt also offers macros for those, QAssert and QAssertX. The second one is similar to the first one, which just gets a Boolean condition and will abort the application if that condition is not true. The second one also allows you to add some extra textual information on the location where that happened and the reason why this assert is there. So what you actually did wrong to trigger it. So in general, whenever you make assumptions in your code, like this pointer can never be 0. No one would call this method with an invalid pointer. Just put the assert there. It will not cost you anything at runtime in a release build. But it will trigger as soon the assumption is violated, and it's much easier to track down what's actually broken than when you actually several lines down, you access an invalid pointer, and you get random crashes or random behavior. However, there's one common pitfall with that. Asserts are removed in release builds. So if you look at that code down here, we create a QFile object. We open that file, and we assume that will always work, right? The file always exists. We maybe just created it before. There's nothing that can possibly go wrong, so let's put an assert there that this works, and in case we violate that assumption, we will hit the assert and will be notified. However, this macro will just evaluate to nothing in a release build. So we are just not opening the file. So all our attempts on trying to document the assumption are actually causing more problems than we are trying to solve. So in general, never put anything into a QAssert that actually changes state, or that basically any non-const method call in there is a problem. So if you just do something like QAssert file is open, that's fine, because it's not changing state, it's not changing behavior of the application. But if you put something like this in, this will cause interesting side effects in release builds. And it's kind of obvious, but it happens to the best of us. Just Friday night to my boss over there. So yeah, that's always something to keep in mind. OK, yeah, now we are getting to the slightly more interesting things, those that are not well documented, the hidden details inside Qt. if you grab through the Qt source code for getEnv, the method to read environment variables, you will find all kinds of interesting bits of code that evaluate random undocumented environment variables, and as a result of that, enable some debug output or do some extra checks. And many of them, unfortunately, only work in a debug build Qt. So it's always good to have a debug build of Qt around as well, because that has all the asserts enabled, especially in model view. And it has all the built-in debugging features enabled. So you want to have that around for testing as well. So let's see a few examples of that. There's Qt Flush Paint and Paint Event and Qt Flush Update. The last one is only for QWS. The first two we will just see in an example. They enable some kind of debug output, graphical debug output for repaints and the areas that are repainted. So if you're debugging performance problems related to repainting, for example, it's quite handy to see what is actually repainted right now and how often is it repainted, and that will enable you to see this. So let's try this. Okay, flush paint, and we just set it to 1. The number actually is the amount of 10 milliseconds it uses to actually display the flickering. Flickering output we are about to see. But 1 is usually fine, so let's use QML viewer. You see a lot of flickering, but now you see, in the end, right, it only flickered in the center part where it was updating, and in the end only at the small sparkling effect at the logo. Let me run that again. So that's quite good, right? It only repaints the areas that are actually changing. Maybe I should show that without the effect as well, so that you see how the animation actually looks like. See, it fades in from gray to black, changes in the middle, then rotates the logo a bit, and then has this small effect on the quick line. Okay, let me go back for a second. So you see it reduces the area it's repainting. So that's actually exactly how we want it. It's only repainting the areas that change. And now you see while I use the menu, it's repainting those I'm actually hovering over because there's a change in style. But it's only repainting the areas that actually need to be repainted. So this is actually a well-behaving application. And let's look at another example on how you shouldn't do it. And luckily, Qt also provides us a demo application for that. Oh, it showed up on the wrong screen, and it didn't. Qt Flash Paint. Oh, there we go. So it's repainting all the time. Well, it has some animation, so that's fine. So let's try to navigate to something where we actually have just a static page. And you see it's still repainting. So that's how you shouldn't do it. And if you have performance problems or lack of or losing your battery, or I should probably disable that. Because of repaints, this actually makes it visible where the repaints happen. So it's quite useful to run your application with that enabled and see what the output actually is. And that usually helps you to quickly narrow down where your repaints are coming from. And it makes it very obvious that you have a problem there, right? . Okay, so let's have a look at another one. Yeah, you might have run into this problem before. You have all kinds of plugins in Qt, right, for SQL drivers, image formats, text codecs, network status checking, and whatnot. And sometimes you might have the problem that, well, you clearly have the DLL for your SQL driver or whatever you want to load there, but Qt it's not picking it up. So you just don't see your SQL driver showing up in Qt. And there could be all kinds of stuff that is wrong there, like search paths does not include the install location. It might have the wrong Qt version, so Qt refuses to load it if the version doesn't match, or if the build key doesn't match. So if you switched from a debug to a release Qt but didn't update your driver, or you built your driver in the wrong mode, then Qt will also not pick it up. And unfortunately, it doesn't really give you a lot of diagnostics on why it doesn't do this. Unless you enable Qt debug plugins, set that to 1, run your application, and then it will print a lot of debug output on what it does with plugins. So it shows you where it is looking for plugins, what DLL it is finding there, and if there's any problem with mismatching versions or mismatching build keys. So that helps you a lot already, but it might still fail without actually telling you what the problem is. And that could happen if your plugin needs additional libraries as dependency. You often have that with the SQL drivers that need, say, the MySQL library to actually communicate with the MySQL server. And to track those down, you usually need to go beyond Qt on the operating system level. But there are similar environment variables, at least on Unix and Mac, to get all kinds of debug output for resolving dependent libraries. And if you have mismatching symbols there or mismatching versions there, this will tell you about it. So in that combination, you should be able to track down most of the plugin loading problems. As far as I know, there is no such thing for Windows. I think there's the depend, or however it's called, to check, just by looking at the DLL if all the dependencies are available. You can, of course, do that on Unix as well with LDD. But this is actually at runtime and involves all the other environment variables you might have set to find your dependent libraries. OK, what else do we have? If you're using dbus in your application, dbus is this, well, mainly used on Unix, inter-process communication framework. Like with any communication, you might want to look at what's actually happening there. So if someone is not replying to your method call, that could be because your call never got out. It might have the wrong arguments, wrong types, so mismatching signatures, or it might be that the other process simply never did reply. And for that, it's very useful if you just are able to see the entire communication. And you can do that by setting the QDebug variable to 1, and then let's just run QDebug viewer. And you see lots of output in the background. That's, the entire communication that happens there. It's not very easy to read. But usually, if you're just looking at, did I actually send out the message? Or does it have the right arguments? Or did the counterpart reply? You will actually find that in there. In this case, all the communication works. And the tool here, QDebug viewer, queries the entire communication. So there's a lot of stuff going on in the background. QDebug viewer, if you don't know that yet, very useful tool in itself as well, because it allows you to check if the interfaces you publish on dbus are actually there, if you can call them, if the replies are correct. You can connect to signals, see if they are emitted on device. So you can simulate the client and test your server with it. OK, let me close that and get back. OK, and we have one more. And that's QWebKit log. That is actually more than just enable disable. That allows you to set a comma-separated list of areas you are interested in. That could be anything from loading, from JavaScript execution, playing media files. So there's a long list defined in the code there. Even in a normal QDebug build, that will not just work, though. Because at least in 4.7, maybe also in 4.6, I don't know, WebKit is always built in release mode, even if you do a debug build of Qt. You have to explicitly ask for also a debug build of WebKit. The reasons why they are doing this is WebKit is really, really large if you do a debug build of it. So we're talking 2 GB of DLLs here. So you need a lot of memory to just link that. But if you have a debug build of WebKit, you can get all kinds of internal information from WebKit as well. Oh, we have one more. OK. If you have problems with media output with phonon, there's phonon_debug, which you can set to 1 or basically anything not empty. And it will print output generic to phonon. So seeing if it tries to play the file, what kind of backend it tries to use. These kind of information, seeing if it finds the codec and all that. And there's, for many of the phonon backends, there's specific debug variables that show you internal details of those specific backends. So if you need more details from there, you can enable those as well. In general, most of this is actually not really documented. You find that by searching the source code for getEnv. And there's actually more than those, so it's worth it to check for that in pretty much every new release to see what nice features that they have built in there. OK, what else do we have? The Valgrind suite. Who here develops on Linux or Mac? OK, who of you don't know Valgrind? Oh, just a handful. That's great. That was very different a couple of years back. So Valgrind is this very, very powerful tool that basically simulates the CPU and simulates the execution of your application and has a bunch of tools that analyze the execution of your application and, well, reports all kinds of errors. However, it unfortunately right now is only available on Linux and Mac. There has been some effort on a Windows port, but as far as I know, it's not working yet. And it only works on x86 CPUs and some of the newer ARMs as well. So I think it works with the N900 and the N9 phones from Nokia. It's also nicely integrated in Creator. We'll see that in a bit. So one of the tools, and I think that's the first one that was developed for Valgrind, is called Memcheck. And that validates all your memory access and memory allocations to see if you're actually accessing memory that is allocated that hasn't been deleted yet. It checks if you accidentally double delete memory. Basically anything you could do wrong with raw memory access. Out of bounds access of an array, anything like that. Very hard to debug with a conventional debugger because the actual effect of that error show up far later than the actual cause. And Valgrind points you right to the source of the problem, the line where you didn't allocate enough memory for the access or something like that. There's not that much to that much specific regarding Qt when using Callgrind. The only thing you might run into is that it produces quite some false positives for some areas in Qt. Anything X11 related, font rendering occasionally shows up, and it doesn't really like the just-in-time compiler for JavaScript in QtScript. Luckily, if you use the integration in QtCreator, that takes care of filtering out all the false positives created by Qt code already. Creator also allows you to create custom suppression files, which you can use together with Callgrind. And of course, you can create your own suppression files for just the Qt noise. But this is actually normal. So if you see all kinds of errors coming from font rendering code, QtScript, anything like that, not involving your code at all, that's usually fine. OpenSSL is another typical source. There's a lot of randomness involved in cryptography, so it sometimes gets confused by that. There's no reason to worry. It's just you need to filter that out if possible and just look at the stuff that involves your code. But yeah, there's a nice integration in Creator that takes care of that. Another very useful tool from the Callgrind suite is called Callgrind. That's an instruction level profiler. So it uses the emulation of the CPU and counts how many instructions you spend in every line of your code. So it gives you a very detailed overview on where you actually spent your CPU time. But it also only shows CPU time. So if you have waiting for I/O, waiting for network, this will not show up here. This is only focused on pure CPU usage. And it's integrated in Creator, so you get some visualization of the results there. And there's also a standalone tool called QGraphics. It's just like Callgrind free software that has much more detailed visualization on where you actually spent your time. So you have the list views sorted by libraries where you can see how much time is spent in each function. You have this space plot up there where the size of the rectangles correlates with the actual time spent there. So you get a very quickly an overview on where you actually spent the most of your time, and that's probably worth looking into. And you have a call graph where you see where the actual function calls are coming from, how often a method is called, and from where. So even if a method is expensive and there's no way around it, another way to optimize that is to call it less often. And this will allow you to track down where actually the calls are coming from. It also allows you to look at, we don't see that in the screenshot, to look at the source code, and it has annotations on how expensive each line is. I think you can even go down even to the assembler level and investigate that. But yeah, that's probably rarely necessary. So now what's Qt specific about this? And let's go back here. And the problem is signals and slots. You probably know that when you look at a backtrace of a slot, or have a backtrace in a slot, you see these QMeta object activate, meta object, meta call, and then the generated mock file, Qt meta call, those 3 or 4 levels of code in between there that's just necessary for the signal slot mechanism. And that's actually getting in the way of Callgrind a bit. Because what you're generating there is like an X-shaped call graph. So if you have one signal that is connected to a slot, you go through those meta object activate, meta object meta call, and then the meta call method in the mock file. And if you have another connection, it goes through the same method. So everything is going through those QMeta object methods. So you can't figure out anymore which slot is called from which signal, which is very important if you want to optimize the number of calls. And it confuses the cycle detection in Callgrind quite a bit. But luckily, there is a solution for that. If you call it in a command line with those magic options, it will filter out all the internals for the signal slot and just show them like a direct invocation, like a normal method call. And then you have a call graph that doesn't involve all this stuff in the middle anymore, and that you can nicely follow which signal is actually triggering the slot and how often. So that's much more useful output. Obviously, that only works for direct connections. As soon as you have queued connections that go through the event loop, then there's no way to track that in a call graph anymore. OK. And yeah, the final tool I want to show here is called Massif. And that logs all your memory allocations and deallocations and basically a call graph where they are coming from. And that way it gives you a heap profiler. So if you want to find out where your memory is allocating all its memory and why it's needing so much, this will allow you to track it down and optimize your memory usage. Unlike the other two, that's not integrated in Creator yet. So you have to run that on the command line, just like shown there. And the output is some complex, unreadable text file. But luckily, there is a nice visualization written in Qt, also free software, that shows you a nice timeline of your memory use. And it has the detailed backtraces at the side. So when you select a time slot, you see where all the memory allocations come from. And then you can start looking into optimizing that. There's a second tab that even gives you a more detailed graph view on where the allocations come from. There's one tiny thing that is specific for Qt profiling there. At least half of Qt uses its own malloc and realloc wrappers that will show up in here as like 50% of your memory is allocated in qmalloc, which is kind of useless, because that is just a wraparound malloc, so you want to hide that as well. And both Massif on the command line as well as this tool give you the option to register custom allocators. So if you add qalloc and qrealloc to that, they will be considered like a normal malloc implementation. And what you then actually will see in the result is where the memory is actually allocated, and you don't have this 50% in my custom malloc wrapper anymore. And it's just one tiny little detail to make the backtraces easier to read. Yeah, there's one big downside of the entire Valgrind suite. It's very, very slow, since it simulates the execution of the program in software. So it simulates the CPU and does all kinds of tracking on top of it. It easily runs 10 times or 50 times slower than usually. And that has some side effects on Qt applications. For example, we don't enter the event loop that often anymore. So if running one iteration of the event loop suddenly takes 50 times as long, we have just just 50 times less opportunities to get into the event loop again. So if your application does a lot of event processing, you might end up with a huge backlog of events in there. Like incoming network traffic might pile up and actually use a lot of memory that it would never use in a real operation. So this is an effect to keep in mind. It will change the results by slowing down the application so much. Not so much for the Callgrind thing, but especially for the memory profiling. And yeah, Q timers will trigger far less often. So if you have an interval timer, it triggers every second. And now it takes 5 seconds to actually get to the point that you can execute the timer. The next one will only trigger after that, so you will only have 1/5 of your QTimer executions, which of course also changes the results. That's mainly something to keep in mind when trying to interpret the results, because in real speed execution, this stuff might actually look a lot different. OK. So next topic. It's not very well known, but Qt actually has two quite complex debuggers and profilers built in for two of its more complex frameworks. The first one we will look at is QScriptEngineDebugger. That's a complete debugger like you know it with breakpoints and looking at watching variables and stepping through code and everything you know from a normal debugger. It even has a complete UI for that. And that's all built in I think, QtScript tools, so you have to link in that extra. And you just need these 3 lines of code to create a new QScriptEngineDebugger. Attach that to a Qt script engine you are using in your application. And what you get is this kind of thing here, complete debugger UI, just 3 lines of code away, and you have a full debugger for JavaScript execution in your Qt application. That comes either as this main window as we see it here, but it also allows integration in your application, so you can access the individual bits of it and embed that in your main window if you want. So you pretty much get a JavaScript IDE for free that you can embed in your application. The other one is QWebinspector. That's basically similar to Firebug, which is, I think, much more known than the Web Inspector. That's a very, very comprehensive suite for debugging and profiling web pages. So that might not sound that useful at first, but if you're using QWebView in your application to show content that is not directly coming from the web, but just for visualizing data from your application, you might still find it useful that you can actually debug the document structure there, live edit it, look at how the style sheets are executed and all those details. And the way to add that is similarly easy than the script engine debugger. You create a new QWebinspector. You set the page on it. The only thing you need to actually make it work is to enable the developer features on that QWebPage instance to prevent that users can actually trigger that in. I think it shows up in the context menu if you have that enabled. So you might not want to have that on by default. And yeah, what you get there is something like this. Allows you to look at the document tree, has the complete interpretation of the style sheet at the side, so you see where the individual properties are coming from. You can live edit all of this and see how it changes in your application. So just to fix the few pixels off in your output, this is very, very handy. Just play around with it until it fits and then change the code accordingly. It also has built-in profilers for page loading speed and shows you nice plots of how the individual bits are loaded from network and how long it takes to execute the JavaScript and, well, all the stuff you might find useful in the context of a web view. So what else do we have? Some useful code snippets for self-made debugging tools, or debugging tools that already someone else made for you, that are similarly easy to integrate but aren't shipped with Qt directly. OK, that's slightly hard to read, but I'll just explain that. First one is called shoeDebug. That's a tiny little Q object which has an event filter, which we will install on the Q application. So the way to actually install that is just Q application install event filter new shoot debug. And then whenever we click on a widget with what is looking for control, so left control click on a widget, it will give us a lot of debug output for that widget we just clicked on. It calls, it shows us the object name, it shows us the class name. It does the dump object info and the dump object tree, all the debug information we saw earlier, just one click away for the widget you're currently looking at. So assume you have a button, you click on it, it shows no reaction. You do the control click on it, you get all the debug information, so you can check, are the signals connected at all? What are the current properties and so on. So very useful to deal with the widget and layouting related problems. Click on an empty space when you try to figure out where is this actually coming from, and it will print you out the widget that occupies that space. So that's probably the one where you have to look for layouting issues. Another one that is slightly more advanced is the model test. You'll find that on the Qt wiki, and there are actually several versions of that out there. I'm not sure if that's the newest one, that's the official one, but there are some other advanced versions out there. So if you Google for modeltest.cpp, you might find some variations of it. And what this does, you just create a new instance of that, put in your custom model, and it will perform all kinds of safety checks, sanity checks, and check for all kinds of inconsistencies you might have added there. So it will walk down the hierarchy, maybe do that twice, compare if you always get the same model index back. It will walk down and will walk up again and compare if you get the same model index back. So it will catch a lot of the typical off-by-one errors you have in your model implementation. And if you hit that, it will assert with information on what actually went wrong. So always useful to have that on your own custom model while developing that, so you catch all the hard-to-debug errors as soon as possible. It will also verify the change notifications you provide from the model. So is the model index you provide in data change actually valid? Is that in the range of the model? Is the insert rows and remove rows, are those consistent with what you get from row count and what you have seen earlier? And that will catch at least 50% of the typical model errors you might run into. It's a larger CPP file, but you can just add that to your project, create a new instance on your model, and you will get asserts whenever you do something wrong. So what else do we have? Right. Oops. Yeah, one more thing. Domain-specific debugging tools. So tools that are created specifically for debugging Qt frameworks, especially the more complex, higher-level ones. So if you ever tried following model view code in a normal instruction level debugger, or trying to get an overview of a graphics scene in GDB or Creator, that is very, very hard, because you're looking at data structures on such a low level that you simply don't get the overview of how the complete thing will look like. And luckily, there are some tools out there that can help with that. And they are all based on the QMeta object system, which allows you at runtime to query information about Q objects, right? So what's their type? What kind of properties do they have? What kind of slots do they have? What signals do they have? What connections are set up, and so on. And you will actually find a bunch of pure object inspectors out there as free software. But there's one Yeah, I just mentioned that. One specific one I want to highlight here because I was involved with that. It's just released on Friday, available as free software on GitHub. It's called Gamma Ray. And yeah, it will give you all the object introspection I just mentioned. But it actually goes beyond that and adds some additional tools that specifically help you dealing with some of the more higher level frameworks. It also has a Creator plugin, so you can just launch your application in Creator and you get the Gamma Ray tool attached already. Otherwise, you can run the application from the start in it or attach at runtime. And yeah, some of the problems you can address with that is, yeah, if you do layouting with widgets, especially more complex layouts, nested layouts, spacings, different size policies, you might end up with scaling behavior that doesn't really match what you expect. You might end up with empty space where you don't expect it. So you want to see what actually the layout looks like there. And what this can give you is something that looks similar to Designer, where you also have the layout overlay, right? But on the running application, no matter if that was using Designer or not. So in this case, we have the Gamma Ray tool here on the right attached to QtCreator. And in the QtCreator configuration dialog in 2.3, I think, there's the page for the settings for the analyzers that has a lot of empty space at the side there. So if we now look at the information that Gamma Ray provides us, we see that there's actually a grid layout in there that has one column too much, one column more than it would need, and it has a row more than it would need. And that's why we have so much empty space there. Now that you see that in here, and you can actually also select the widgets that are in the empty space there, it's very easy to fix that. Yeah, when dealing with graphics view, especially if you have a large scene and you start to do transformations in there, especially rotation, that is the one I always get wrong. You might have the wrong transformation origin, or you have a wrong idea on where your coordinate system is, and then you just rotate your item completely outside of your view. So you run your application and you don't see anything. So what went wrong there? Am I drawing behind? Is my painting not working? Or if I just done a wrong transformation? So it would be nice if I can actually zoom out and look at everything there, find my items no matter where they are, look at their properties, look at their transformations. Yeah, check there. That's another common problem is I draw my custom item, but parts of it are missing, or if I click on it, it's actually not going to my item, or I click on some empty area and it's going to another item than I expected. And usually the reasons for that is wrong bounding vectors or wrong shapes. So it's very useful if I can just see what the item reports as bounding vector as shape. And we can do that as well. So here again, we have the QML viewer with its empty demonstration running, and we have the Gamma Ray tool attached. And it shows us the graphics scene tree up there, so we can look at the structure of that. We see all the properties of the items at the side, so what's their position, what's their transformation, what's the transformation origin. And we see in the second view down here, it's hardly visible in the center, the red dot, that's the transformation origin. So if I rotate, that's how it's going to be rotating. We have the bounding rect and the shape. In QML, every shape is also a rectangle, so it's always overlapping with the bounding box. We see the black lines in there for the coordinate system. So it gives us a lot of extra information when dealing with the graphics scene. And I also can zoom out there and see items that got lost somewhere in the outside. Yeah, model view I mentioned a few times already. It's probably the most complex framework in Qt, so it's also the one where you could probably use tool support the most. And it gets especially messy when you have proxy models or even a large cascade of proxy models. And one of them is doing something wrong, and then you have to look at all the intermediate steps to find out which one is behaving differently than you expect. Because just from looking at the final result, it might be very hard to figure out where stuff get actually messed up. And that's what we see on the left side here. That's the complete model tree of the application on the right here, KML Mobile. And yeah, on the top level, we have the actual models, and all the nesting you see there are proxy models. So there's a lot of proxy models involved there, and I can select each and every one of them, look at which data they pass through, how they transform it, and look at all the roles that come out of it. So it helps me to narrow down the proxy model that's actually misbehaving in my model stack. And yeah, I think the final one, QTextDocument. You might know that from QTextEdit, QTextBrowser. But if you look into the details of it, it's actually a surprisingly complicated structure. It has a document tree of elements, yeah, somewhat similar to the DOM tree in HTML. So it has frames and blocks and fragments and lists. All of these are classes, and all of them have their own format properties. It's quite hard to get into that and to get a feeling for how is your document structured. So where do I actually need to do manipulation that it shows up in the way I want it. And yeah, Gamma Ray has a text document structure viewer as well. So over there on the left, we see the internal structure of the QText document showing in this application on the right here. We see a second view of the text inside Gamma Ray that is highlighting the current element we are looking at. So you can look at all the layouting properties, like what's the bounding box of it and so on. And down there on the left, we see all the format properties for that specific element. So you see how font settings propagate through the document, for example. And it can do several more things. It has a state machine visualization that actually got only done Friday afternoon, so I don't even have it in the slides, but it's running on our booth and a demo. And it allows you to look at several other resources in Qt, like the QResource built-in file system in the application, for example. So you can check out if your resources are compiled in the correct location. It can test the QText codecs Qt found. It shows you the fonts Qt found. And it allows you to attach the QScriptEngineDebugger and the web inspector we saw earlier. So you don't even have to write the 3 lines of code. You can just runtime attach it using this tool. OK, I think I'm running out of time anyway. So that's it from my side. Are there any questions?
Can you use your tool to debug JavaScript code from inside Qt Quick applications?
The QtScriptEngineDebugger doesn't really work with QML. You can attach it on its Qt engine that's used internally there, but usually since the calling order is kind of undefined, that's not the best way of doing it. The latest QtCreator has a built-in QML debugger. That, at least to some extent, allows you to debug that. I'm not sure how well that works with more complex JavaScript, but that's the first one I would try. So that covers most of the QML-specific things. We will see a bit more about debugging QML specifically in the next talk. Nothing? OK. Thank you.